So we're going to continue looking at sampling distributions. And essentially what that does is that if you get a sample, just one particular sample, you can use it to create an interval where you believe the true answer to the population value is. So let's do a kind of overlap question, then we'll move on to what this is doing. Let's suppose we're interested in the percentage of adults who would vote for candidate A. And we collected a sample of 2,000 eligible voters. And our sample, which I'll just call P1 hat, we got 1,075 of them said that they would vote for candidate A. And in this case, 1075 divided by 2,000 comes out to be 0.5375. Since I like percentages, that's about 53.75%. So we could, just based on that information, make a kind of reasonable conjecture, and say, I think candidate A is going to win the election. Provided I've made sure that this was a really good, fair, representative sample, right? I didn't go to places that I knew candidate A was popular in or whatever, right? It was pretty mixed bag, everybody, right? Then that would be a reasonable assumption. But we know from practical experience, every time you take a sample, don't you get slightly different answers? You know, I could have taken another 2,000 people and it might have only been 51%. And then I do it again and it's 49%. Isn't there some variation going on? So we created a thing called a confidence interval. And what that basically does is it gives us a range, an interval of values that we believe the real answer would be. And we typically have, one of the most common ones that we have is a 95% confidence interval. And a 95% confidence interval is given by p hat plus or minus 2 times the standard error. Now, in this case, we know what the p hat is. It's 0.5375, give or take 2. And this standard error guy is also called the standard deviation and a couple of other names. He has a very special formula. Any volunteers, just by pure memory, what is the formula for calculating the standard error of a single sample?
Square root of p times 1 minus p over n. Right.
And in this case, I'm calling them P1s and we're putting little hats on. Sometimes it's P, isn't it? Sometimes P hat, it depends on the story. But it's the same formula, right? Whichever version of P they give us. So in this case, it's going to be 0.5375 times 1 minus P, which is what you get when you take this away from 1. So it's 4625. All divided by a sample size of 2,000. And we now go the square root of 0.5375 times 0.4625, all divided by 2,000. And we get 0.0111. To 4 decimal places. So I'll now return back to my calculation and it's going to be 0.0111. And so my 95% confidence interval is this guy plus or minus that guy. And you take this away from that and you get 0.5153. And you take this and you add it to that and you get 0.5597. And that's the guy that we call a 95% confidence interval. And since I like percentages, 51.53% to 55.97%. So our prediction is based on this sample that that guy is going to get in the election somewhere between 51.53% to 55.97%. That is our prediction. So if that was happening right now, wouldn't we have a headline, candidate A is probably going to win the governor's election or whatever it would be? Right? Now, we can't say for sure because the election hasn't happened, right? And all sorts of things happen in real life. But based on what we've got, that's our best guesstimate, isn't it? So let's look at this in a little bit more detail. The reason why he is going to win is, in this case, isn't everything over 50%? And you need more than 50%. Actually, don't you need 50% and one more person to win an election? Right. The second thing is this fella. This is a 95% confidence interval. That means that we are 95% sure that this interval contains the real answer, right? What's going to happen in the future, right? But if you turn that on its head, doesn't that also mean that there's a 5% chance that this interval is wrong? Now, if there was 20 state elections, right now today, if 20 different state elections were happening, and I used this confidence interval, wouldn't I, just by sheer probability, wouldn't I get one of my 20 predictions wrong? Right, one of my 20 intervals wouldn't actually have the real number in it. So I might predict quite correctly 19 of the results, but couldn't I also wrongly predict one of them? And people think because you wrongly predicted one, that somehow that's a suspicious thing. You went and said that candidate A was going to win Wisconsin and candidate B beat him. There's something going on there. That's not true. Isn't that actually what you would expect from this process? That if you're using 95% confident intervals, which my gut feeling is telling me that's probably what they do on TV when they, they do the show. They had one last night, didn't they, about the, I think it's Virginia and New Jersey, right? They had the show about the elections that are happening there, right? They had people collecting percentages, and they collect percentages of all sorts of things, right? And eventually they got to a point where they were comfortable enough to predict the winner, even though theoretically they were still counting votes. They kind of knew what was going to happen, right? They can get that wrong. I can never remember who it is. I wish I had a good memory, but I don't. Wasn't there a way back in the day a false prediction that one of the presidents was going to win? And I think Hoover or Jackson or whatever, one of the presidents actually did win. It was way back like in the 30s, right? The newspapers had said candidate A was president, and they printed papers, and then actually candidate B won. So they do, even to this day, make mistakes. So they've been doing it for a lot. That in itself does not mean that anything unscrupulous is going. So don't be fooled into, because a guy didn't win and you predicted that he should win, that somehow that is evidence to prove that something nefarious is going on, right? It just happens. In this case, it's happening 1 in 20 times roughly. Now, I could improve in that. Couldn't I do a 99% confidence interval? And I won't go through the details of it, but let's suppose I did it. And it ended up being 48% to 60%, just for argument's sake, right? Now, in a 99% confidence interval, there's only a 1% chance that I'm going to be wrong, agreed? But I'm still going to be wrong 1% of the time. Unfortunately, isn't 50% in this interval. If this was the confidence interval I was using, wouldn't we have to say too close to call? Because if it's 48%, didn't the other guy win? And if it's 58%, didn't candidate A win, right? And if it was 50%, God forbid that ever happened, don't they do a recount so they can find one vote more for one guy compared to the other? I don't think it's ever happened in the history of any country that you got 400 million, well, that's an exaggeration, right? 400,000 for A and 400,000 for candidate B, right? It's never happened. But I guess if it ever does happen, don't they just do the election again? I don't know what else you could do. So what happens when you increase the confidence interval? Doesn't this get bigger? Not only does it get bigger, doesn't the chance that you get it wrong get smaller? There is a 99.9% confidence interval that is hardly ever used. It tends to be used only in situations where you are really want to be absolutely certain, as far as you can be, you didn't screw up. You know, things like sending rockets into space, you know, that kind of situation where you don't want to be wrong even 1% of the time, right? If you did that one, wouldn't the interval just get even bigger? Does it make sense? If you want to be 99.9% sure, don't you have to have a massively big interval to make sure the real answer is definitely inside? Now, you could go the other way. If I did a 90% confidence interval, although I haven't calculated, can I tell you I know for certain that it's going to be smaller than this one? You might get numbers like, I'm making this up, 55 to, well, it's 53 there, so let's make it 51 to 55. How about that? Now, it's a very narrow interval, but aren't you going to be wrong 10% of the time? So there's almost like a seesaw effect here. As one of them gets bigger, doesn't the other get smaller? Right? As one goes up, the other goes down. So you can't have both at the same time, right? You can't be 99.9% sure and have a tiny interval. But you agree that that's, you know, you can have a big interval, right, and be really sure, or a small interval and be really big, if you've only got a fixed sample size. What would happen if you did the same experiment, the same result, whatever you want to call it, but the sample was 2 million? What do you think I would get as a confidence interval if I did the same process as this one, but with 2 million people instead of just 2,000? What would you predict would happen? Agreed. Wouldn't the interval narrow down to the point where, you know, it's like, well, 5.3 to 53 to 54, right? It would be tiny. So the moral of that story is choose big samples. So now let's do the next fella. We are going to now look at the difference between two proportions. And we're going to do it by hand. And then once we finish doing some of these guys by hand, we'll look at some of the homework questions and we'll look at some terminology as well. And then hopefully today, but if not today, definitely on Friday, we'll say to you, this is a lot of work. Wouldn't it be nice if Salt could do it all for us? And I'm going to say, yes, it is. And this is how you do it. But the reason why we're doing it by hand and going through the whole process is so that when you do Salt, you can say, yeah, I know how you do it by hand, but this is much quicker, right? So you understand what is going on underneath the software, right? So now imagine you've got two groups. We're going to have Scotsmen against Americans. And we're interested in what's the difference between the two. So we find out, and we'll call the first sample sample 1, and we'll call this sample 2. And we asked 500 Scotsmen, did they get drunk last week? And 350 of them said they did. So 70% of Scots people got drunk last week. Just to be stereotypical. And they asked 1,000 Americans, because for whatever reason you asked more of them. And out of that 1,000 Americans, 600 of them said they got drunk, which is 0.6. I want nice, easy numbers as well. Would you agree that there is some evidence that Scots people get drunk more than Americans? But couldn't that just be caused by the randomness of samples? I mean, couldn't I do another sample of 500 and it ended up only being 62%? And I did another sample of 1,000 Americans and it ended up being 64%. Each one varies a little bit, don't they? Each sample always varies a little bit different, right? Hopefully close to the real answer, but sometimes far away. And so we have to have a way in which we can create confidence intervals of the difference between them, right? So we have a fella called the standard error. And it's called the standard error of the difference. It's basically a number that tells you how spread out the difference between the two is. And here is the ugly formula for it. Does that formula look sort of a kind of familiar? If I rub that guy out, isn't that the formula that we used earlier today? Can you see all you're doing is adding the two together inside the square root? So although it is ugly, it kind of makes sense that that would be a reasonable thing to do, right? You're combining two things that are varied. So you probably are going to add their variation in some way, right? Combining them. So in this question then, it's going to be 0.7 times 0.3 divided by 500. Add 0.6 times 0.4, all divided by 1,000. And this is where calculator takes over. And the square root of 0.7 times 0.3 divided by 500 added to 0.6 times 0.4 divided by 1,000. And we get 0.026 to 3 decimal places. And let's just stay on the 95% confidence interval. And the formula is P1 hat take away P2 hat plus or minus 2 standard errors for P1 hat take away P2 hat. Now, If you take P1 and P2, which is 0.7, take away 0.6, that difference is positive 0.1. Give or take 2 lots of this guy. So it's give or take 0.052. And if you take that away, you get 0.048. And if you add it, you get 0.152, which is 4.8% to 15.2%. So we have now calculated a 95% confidence interval for the difference between these two groups. Do you notice that these numbers are all positives? Agreed? That is important for the last part of this question.
Quick question. Wouldn't that be
Yes.
4.8%? Not, oh, there is a point. I didn't see that. Okay, sorry.
No, well, it's worth checking because I do forget things. Right. So since this interval is all positive, doesn't that make P1 bigger than P2? Would you agree that's what that is telling us? Right. If P1 take away P2 is positive numbers, then doesn't that make P1 bigger than P2? That's what I'm saying. Does that make sense? So what we've got here is that Scots people drink more than Americans, and we've got some evidence to prove it. Roughly, don't Scots people drink between what, 5 and 15% more than Americans, according to this data, right? The difference is how much more. Now, there are 3 distinct types of answers you get. You get the answer where everybody is positive. And that means whatever the first thing is, it's bigger than the second. Sometimes all the numbers are negative. That can happen too. What do you think if the differences are all negative numbers? What do you think the connection between P1 and P2 is now? If when they're all positive, the first guy is bigger than the second, what do you think it means when they're all negative percentages?
P2 is bigger than P1.
Which I'm just going to rephrase that way, but it's correct what you said, Eric. P1 is less than P2. It's just another way of saying P2 is bigger than this one. I'm just trying to keep them in the order P1 and P2, right? So that's the same thing. No, P1 less than P2 is not the same thing as P2 is bigger than P1. Yes.
Just being difficult.
No. And then you're going to get this one. Whenever you see an interval like that, you'll see the phrase it contains 0. Now, what that means is that the interval contains negative numbers and it also includes all the way up to positive numbers. So would you agree 0 is in that interval somewhere? When that happens, there is no evidence to prove they are different. So we can't say for sure that the first thing is bigger than the second thing, or that the first thing is less than the second thing. Couldn't it be one or the other? It could be any of these numbers, right? If the difference is negative, that's true. If the difference was positive, the top one's true. If the difference is 0, doesn't that make them equal to each other, right? There's no difference at all. But we don't have any evidence one way or the other to prove they are different. So that last one is not good. Not good because we don't like it. And let me introduce a term. You see this guy here? Does anybody remember what name we give to this decimal that you get here, sometimes a percentage? 3 words.
Is it the margin of error?
That's the one. If any of you are into politics and they're doing polls, isn't it within the margin of error or some phrase like that, too close to call? You heard those kind of terms. They're talking about the fact that the interval looks something like this. We don't know. This one, wouldn't the first guy win? If this was the interval, wouldn't the second guy win? If this is the interval, nobody knows who's going to win, right? Too close to call. Any questions about that? It's just an expansion of what we've done to now include the difference between two proportions. Are we good? Right, let me see if we can do a class quiz then. Okay. I'm going to split you into two groups. Self-identified males, self-identified females. Let me do a count on how many of each we've got. 1, 2, 3, 4, 5. That's not good. There's 6 males in this class. And 18 females. Wow. Very small samples, but we're still going to do it. And I'm going to ask you a question, and we're going to get a P1 hat, and then we're going to get a P2 hat. And we're going to see if there's any evidence to prove, is there a difference between males and females, right? So let's think of something that you're likely going to, honestly answer. And something that might have a difference. Try to think of a sexist thing to ask. Okay, I'll try this one. If it doesn't work, I'll try another one. How many, this is just for the males right now, how many have a truck? Not a good question. Pick another question. All right. How many of you like watching science fiction? Do the little handies. 1, 2, 3. I need some hands. Those, where we go. 1, 2, 3, 4. 4 out of 6 guys. Okay. Females, hands if I can't see you now. How many like watching science fiction? 1, 2, 3, 4, 5, 6, 7, 8, 9. I make it 9 out of 18. Okay. So that's about 0.67 roughly, and that's 0.5. Would you say that very superficially, because there's not a lot of data here, but would you say it seems reasonable at least? If and if I didn't count you, I'm sorry, but we're just going to. Actually, for the data, it's probably a good idea I didn't count some of you. Would you agree superficially it looks like males like watching science fiction more than females? Very roughly. So let's create a 95% confidence interval. Before I do that, I need to calculate one of these guys again. I won't write the formula this time. It's the same guy as here. I'll just go 0.67, 0.33 over 6, and 0.5 times a 0.5 over 18. And the square root of 0.67 times 0.33 and divided by 6, add 0.5 times a 0.5 divided by 18 gives me 0.23. So our 95% confidence interval is going to be P1 hat take away P2 hat plus or minus 2 standard errors. 0.67, take away 0.5, plus or minus 2 lots, say that guy. So 0.17, give or take 0.46. Not looking promising, guys, is it? Negative 0.29 up to 0.63. So that's negative 29% all the way up to positive 63%. Wouldn't that be not enough evidence to tell if there's a difference? And the reason why I would do that is, would you agree that this interval, they phrase it like it contains 0, right? But doesn't it contain negative and positives as well? Why did we get such a horrendously ugly margin of error? Why was the margin of error 46%? You stop your hand up, Isabel, now. Why was it 46%?
Because our pool was tiny.
Yeah, our pool was ridiculously tiny, right? But did we at least get the process that this is how you would go about it? Let's just pretend that we got lucky. If that had came out, it might have, right? Would it not mean that guys watch sci-fi more than females, and we've got some evidence to prove it, right? It's at least bigger than 0. So that would be guys more than women. Of course, it could have been negative 15, right, to negative 1%. Wouldn't that be actually evidence that they don't watch sci-fi as much as women? And then this one can't tell if there's a difference. Okay, now that you've seen 2 of these, do you get the feeling it's a kind of the same old, same old? They just change the numbers, but the process doesn't change much, right? You're going to have 2 groups with some data. You're going to collect enough data information to get the standard error. Typically, they're like 95% confidence intervals, and then you can very often you make a conclusion based on what that interval says. Let's look at the homework. There's some stuff here that we want to talk about as well, but I think it's better to see the question than to hear it. I wonder if I can make this bigger without losing the edge. No, I lost the edge. Okay. So in question 1, the populations are males and females, registered voters in America. And we're interested to compare the proportion of each group who registered with the Democrat Party. And suppose in truth, 28% of males and 35% of females, that's the truth. And you get a random sample of 700. Let the first population be males and the second population be females. And we are being asked here, for each of the following situations, specify the mean of the sampling distribution, which is them basically saying, what would P1 take away P2 be? So in this question, 28% take away, males first, wasn't it? Let's check. Yeah, so take away 35%. And won't the answer be negative 7%?
Phoenix, be quiet.
Are we good with that? It's actually not a lot of work to be done in that one. And the other 2 are very similar. Now, in question 2, you are given P1 hat, you're given P2 hat, and both samples are both 700. Isn't this just going to be practice at getting the standard error? So you're going to do that square root of P1 hat, P2 hat, you know, all that stuff, right? Do you want me to do one of these three, or are we good? It's just plug and chug into an ugly formula. Do you want to see one of these or not?
I'm good.
You're good. We'll move on then. The next bit I need to leave for a moment because we haven't covered it and tell you what it's about. We haven't really spent a lot of time yet talking about when you can do all this confidence interval stuff. Can you just do it with? No. Would you agree that you need an unbiased sample? Right. It wouldn't be a good idea if I was interested in, say, the Scots and American drinking thing. If I decided that my sample in Scotland was only going to be taken from people that I spoke to who were leaving pubs, and then the sample in America, I only spoke to people who were leaving church. Would you agree that those samples are totally biased, right? You're not asking a fair representation. So we're assuming that it's unbiased. But the second one is a little bit less obvious how you can check for it. Shouldn't we have, for want of a better word, a big sample size? Would you agree that the one that I did with you lot was horrendously small and probably very dangerous to use to predict for all of America, right? Far too small. Now, we could just say, make your sample, bigger than 1,000, but that's not how they do it. N1P1, N1, 1 minus P1, very often with a little hat on it, N2, P2, and N2, 1 minus P2. Those 4 calculations, all of them, they have to be bigger than or equal to 10. If any of, so you've collected 2 different samples, right? The guys and the girls. If any of them come up with a number that's less than 10, you are not allowed to do confidence intervals, and you shouldn't be doing them, right? I know physically you can do the numbers, but any answer you get is irrelevant. Nobody cares because it's not useful, right? In that previous one that I did, I don't know if I've got my data handy. I don't know if I've got it anywhere here. Yeah, here we go. If you did this guy here, right? Just for example, it was 6 times 0.67, and that ends up being 4. Do you see I should have stopped there? If you're wondering what these numbers are, this is the number of people who said yes, and this is the number of people who said no. And this is the number of people who said yes from the second population, and this is the number who said no. So you must have at least 10 people to say yes and no to whatever the question is. Are you going to vote for candidate A? There must be at least 10 people who said yes and at least 10 people who said no. And that's what question 3 is all about. And they give you as a story here. What did they say? Right, well, I'll just show you. I can't really read it out. It's one of those choice things. Let's see what it looks like. Right. For each of the following situations, explain whether the conditions hold for doing a confidence interval, essentially. Right. The sample proportion are taken from 2 independent samples, which I'm assuming they are. So in other words, the unbiased things taken for granted. Selected at random from the 2 populations of interest. All these combinations, right? See these guys here? Are probably at least 10, right? 10 or more. Thus, we find the conditions are probably men. Right? So that's kind of how they phrased it. Now, they never gave me real numbers to check it, but would you agree if you asked 1,000 women almost anything, you're probably going to get at least 10 of them to say yes, right? And 10 of them, at least 10 to say no, right? You've got 1,000, no matter what you pick, isn't the other one going to be pretty big? So I think that would be a reasonable assumption. And here are some others that you can pick and choose from. So wouldn't it be nice then if we could do this calculation without all that number crunching, right? Without all that ugly square root and multiplying and so on. So here is a story, which I hope you're looking at, is question 4. Can you see it? Right. There is some evidence that women tend to vote earlier in the day than men tend to. And if men and women vote differently, then the exit polls in the day may not reflect the eventual results. Have you ever, you know, if you're into politics, which may not be, when they do exit polls, basically they ask people who've already voted, how do they vote? And you hope that they're honest. And they do them like at the morning and the afternoon, and then they might even do an exit poll right at, you know, before closing to get a kind of spread of where the data's going. According to this, at least, women tend to vote earlier than men. And men and women don't actually vote quite the same. Excuse me. Does anybody know roughly? Do women vote more Democrat or more Republican? In general, of course, all things change, but in general. They tend to vote more Democrat. It is what it is. Men tend to vote less so. So there's a definite difference. So if this is true, won't the voting favour the Democrats in the morning and then favour the Republican candidate later in the evening? So there's going to be just a natural change, not because anything weird is happening again, right? But just that's the way these things go out. So what do we have? We have, I better write this down because I'll lose it. 53% of the voters in the morning candidate, 49 candidate, the exit poll survey, 500 in each case. So I'm going to find 53% of 500. And then that's for the morning people. And for the evening people, it's going to be 49% of 500. So if you bear with me for a few seconds, 53% of 500 ends up being 265 out of 500 people. And the 49% out of 500 ends up being 245. Now I need the data to be in that format. So 53% is no good for SALT. It doesn't want to know that. 0.53, although it's better, it still doesn't want to know that. The way SALT works is you have to say how many people out of how many. So 53% out of 500 became 265 out of 500, and that's what I'm going to use. So I'm now going to click on the SALT button, and I'm going to bring this guy over to here. And in inferential statistics. Do you see inferential statistics, my little mouse on it? That's the guy you pick. Now you click on this one and you see two sample proportion, right? Click on that. Now, number one was the morning people, and that was 265 out of 500. Sample two was the later in the day guys, and that was 245 out of 500. Okay, let me pause there. Are you happy? Population one, population two. You happy where I'm getting these numbers from? Right? That there is basically the 53% out of 500 in the morning, and that's the 49% later in the day. You then scroll down and you hit this guy, confidence interval, and hey, that's the one I want, right? 95%. And then you hit generate results, and all the good stuff is over here. For instance, the difference between those two is 0.04. Do you know that ugly standard error thing? That's the number there. The thing that they're calling the lower limit and the upper limit, those are your intervals. So if I take this number here first, where's my interval going? Okay, this question doesn't even ask for the interval, the little darlings. Can we pretend that question did ask for the interval? Then wouldn't it be negative 0.02197 to 0.10197? So that would be the small number, comma, and that would be the big number. Do you see how your interval is there? I wish they'd actually ask for that. And what do they ask for? They ask you for this one. They ask you for that one. They ask you for that number. They ask you for that number. I mean, they ask you for various numbers. What they don't ask you for right at the end, which is what I would hope for, would be that number or that pair of numbers. Okay, so let's make up one. Suppose I have a story and I've got two populations and I want to compare them. And in the first population, we asked them, and 512 out of 1,100 people, right, said that they like sci-fi movies, and that's the males. And 524 out of 1,300, that's how many women said they like sci-fi movies. So can you pretend that was my data? You see how you write it in? How many liked it out of the total? How many liked it out of the total? There's a 90% confidence interval. Now generate the results. Can you see that this would be between 2% and 10%? Wouldn't that be evidence that males do like watching sci-fi movies? Now, what would happen if I went here and I just changed it to a 99% interval? Do you think these numbers would change? Wouldn't they get further apart? So wouldn't that become smaller and this becomes bigger? Let's find out. And they did. Now it's 1% to 11%, right? It moved out just a little bit. But aren't they still positive? And that was a 99% confidence interval. So this was real data. Couldn't I be pretty comfortable that men do like watching sci-fi more than women? Right? Now, I don't want to bet my house, so I'll do a 99.9% confidence interval. Would you agree that that makes me pretty much bet your house on it? You're probably going to be right. Well, let's see what that generates. Oh dear. Do you see that little horrible negative number at the start? Doesn't that mean we don't have evidence at this level to tell for sure that men watch it more than women? So do you see the confidence interval that you use can actually reflect, can affect your conclusion? In a 90 and a 95, wasn't I quite happy to say guys liked watching the movie more than women? But when I went to 99.9%, the evidence wasn't there. Can you ever have a 100% confidence interval? Is there any situation where you could get 100% sure? In reality, in real life, no, but theoretically you can. How about this as my confidence interval, 0 to 100%? Wouldn't that guarantee that the answer was right? or minus 100, I should say, since it's 2, minus 100 to plus 100. Would you also agree that interval is useless? Tells you nothing. Any questions so far? Are we good with the salt band? You like it much better. And there's some pictures there, but they're the least of your worries. That one's pretty much the same kind of story as the one before. And that one, oh, here's one. In this one, you don't need salt because actually all the information you need is here. So it's just a matter of how do you read it off. So in an ongoing nationwide survey, a question asked is whether a respondent favors or opposes the death penalty, right? And in 2008, 635 out of that number, which is 32% roughly. And then in 1993, it was this out of that, which is that number. And they even tell you what the difference between the two is, which is basically if you took that number and subtracted that one, you would get that, right? And a lot nicer, can you actually see a 95% confidence interval the way you would want to see it, right? So this isn't what SALT does, but there are lots of statistical software packages that do things that look much more the way you want them to look, right? Nice little table, nice little interval with brackets and everything, right? Now, don't overthink this. What proportion from 2008 opposed the death penalty? So these are opposing the death penalty. What proportion in 2008? It's in that table. Just tell me what the number is.
0.327.
Would you agree it's this guy here? And being lazy? Couldn't I just do that? Now, when you want to do 1993, would you agree it's this number? Now, they've called it not P1 takeaway P2, and they've not called it P1 heart takeaway P2, but would you agree it's still that number? And is it the confidence interval? Those guys. Well, yeah, it's those guys, but I guess I'd have to move them around a little bit. I think that was a 5. This is a 95% confidence interval. Does that mean we are absolutely 100% sure that the right answer is somewhere between those two? No. Aren't we just 95% sure it is? So one of those sentences is the one you're going to use. Now, if you went and did the horrible formula one, the guy that would be using is the guy that looks like that one, isn't it? Do you know that there's no numbers attached to it? It's just generic, but that isn't that the formula? P1 heart, take away P2 heart. In our case, wouldn't we be using 2 here and then the other stuff? And
Wait a minute, is that the
Is
right? Wait, I think the top
oh,
one
there
is
are
right.
P2 and 1. Yeah, I misread it. Thank you.
Okay.
Yeah, because it's 1 first and 2 second, and I don't know what that is. It's a mixture. That's a monster formula. Doesn't work. Now, this one here has all the numbers in it. Have you noticed that it's not 2, but 1.96? You see that? We do by hand 2 because we're doing the empirical rule, which is a rough, rounded off kind of thing. Isn't 2 1.96 when you round it up? So it's not that it's a different formula. It's just a little bit more accurate. SALT, because it's, software, can't it do things to 20 decimal places if it wanted to? So it can be really accurate. So that's the only difference with that one. Do Do you want me to do another one from this, or shall we move on to the next section? Do you want to do an? Thumbs up means we're moving on.
No,
Want to see it?
can you do one more?
One more. Okay.
Thank you.
I'm staring at this one, so we might as well do it, right? Which is what, question 9? So I'm going to have to write the numbers down so I can keep track of them all. So 85 snorers out of 1,105 have heart issues. So that's going to be my P1 group, 85 out of 1,105. And my second group is 29 out of 1,379. Okay. And they want a 95% confidence interval. So click. So inferential statistics, hit the button and choose 2 sample proportion. And the first group were the snorers. So that was 85 of them out of 1,105 had heart issues. The second one were the non-snorers, and 29 out of 1,379, those had heart issues. Confidence interval 95, good. Boom. So that's my lower limit and that's my upper limit. Agreed? Right. So I'll put them over here and take the first number, copy, put it in there. And the upper limit, as they call it, is the second number in my software. And I'll put it in there. And then I'll read the answer, and they want 3 decimal places. So I'll round that to there. And they want 3 decimal places. So I'll round it to there. So the difference between snorers and non-snorers, right? If you subtract one from the other, the difference between them is about what, 3.8 to 7.3%. Agree, all positives, right? On the basis of this, could you determine that there's a difference between the two? Well, I would say yes, you could. And yes, because the interval does not cover 0, which is a funny way of phrasing it, but that's how they do it. Would you agree all those numbers are positive? If it covered 0, it would mean 0 would in the interval. That's how they phrase it. I would have phrased that question differently. Would you agree there's enough evidence to prove that snorers have a higher heart issue rate than non-snorers? Right? Because the difference is positive. First one bigger than second. And there's another one, men and women. And here's another one, men and women again. We need a joke before I start the next one. I need a joke. Anybody got a really bad joke while I'm getting myself ready for the next section? Anybody got a good joke then? Maybe I'm asking the wrong question. Abra, you got a joke?
I do not have a joke.
You're just not trying hard enough, right?
I am not quite awake today.
Okay, well, that's not what I'm looking for. I'm looking for chapter 10 here. There we go. That's better. Who have we not picked on? Did I tell you the one about the big oil fire in Texas? Okay. Well, there was a huge oil fire, and the owner phoned around to every, company in America and the world that put out oil rig fires. Very specialized job. And none of them could come. They're all busy. And he phoned up the last company, and the guy said, no, we're busy for the next 3 weeks. We can't help you. And the guy says, look, I'm losing a fortune here. This thing's burning away. I need somebody to put this fire out. Is there anybody? I'll take anybody. I don't care if they're new or what. And the guy says, well, there's this new Scottish company that just started. Says, I wouldn't use them. They're a bit of cowboys, they're not very good. They don't have anything. They've no experience, anything. Texas says, give me their number, I'm desperate. So he phones the guys up, and Scott's guy out there and says, not a problem, we'll be there tomorrow. So early in the morning, the Texan guy is waiting at the bottom of the hill, and he looks at the top, and sure enough, these guys are all up here, these Scots guys up here, and in this beat up truck, and there's about 12 of them in the back, and you know, the guy in the front driving, and comes down the hill. He's waiting for them, and they start getting faster and faster, and instead of stopping, they zoom right by the Texan, shoot straight across the plains, smash the truck right into the oil rig, knock the thing over. The guys in the back jump out. Some of them are on fire, and they're rolling about to put the fire out. And then they grab, you know, spades and shovels and brooms and everything, and they batter the fire out with their bare hands. 1 minute, the whole thing's over. And the Texan's just amazed. And the Scots guy, the owner, comes up, and Texan's signing the check, and he hands it over. And he says, oh, I've never seen anybody put a fire out like that before. And he gives him the money, and he says, what are you going to do with that check? And the Scots guy looks at it and says, do you know, the first thing I'm going to do is get brakes for that bloody truck. Two of you liked that joke. After all that hard work, I get two. Abra, come on, help me out here.
I laughed. I thought it was funny.
Okay. Barbara, was that funny, or was that up to my usual standard?
I think usual standard.
Okay. At least you're honest. Right. It gives me a chance to get my brain together. Right, everyone, we are moving on to chapter 10. The good news about chapter 10, if there is such thing, that's not where I should be, is that it is really just a continuation of previous information. So they're doing a lot of revamping. Hopefully, are you lot now looking at question 1 from chapter 10? Right. So they're going to talk about things that you've met before, and we're going to use salt towards the end. I'm not sure if we'll get to the salt part, but we'll definitely do it on Friday. So in each of these questions, explain whether the proportion that's being described is a sample proportion. That means you got the data from a sample, or is it a population proportion? And in the first one, in 2010 US Census, it was found that 1 in 8 Americans was 65 or older. Okay, did that proportion, is it a sample proportion, right? Or is it a population proportion? Correct. What was the clue?
The census.
End of story, right? So you're not going to overthink these. But by the way, there are only 2 choices, right? So it's not like you've got a lot to pick from. Let's do the C then. In a clinical trial on asthma, a satisfactory relief from symptoms was experienced by 56% of the 90 participants. Is that a sample proportion or a population proportion? Agreed. Fingers up, number 1. Would you agree? You've seen enough of them now. Aren't most questions pretty obvious if the information's about a sample or it's about everybody, right? If it's about everybody, it's a, you know, it's a population thing, right? If it's, you know, a little group of people that they're asking, you know, it's a sample. That's essentially what that is. Now, the next one, I guess question 2 here. A survey is done to estimate the proportion of American adults who think that texting while walking across an intersection should be illegal. What's that? What's the population of interest? And think like a lawyer. Every word's important. And I'm going to direct your attention to here. Nope, I can't see. Somebody say it out loud. Okay, I can see an answer. It says all US adults. Why is it not everyone in the United States? Because it could be in a different story. Can you see proportion of US adults? Isn't that what you're interested in? So if you know what you're interested in, don't you also have inside that who you're going to ask? In other words, who your proportion is, right? Who your population is. These are pretty easy, so I'll skip by them. This one is easier than you think. What is the likelihood that a 95% confidence interval will not cover the true population value?
Is it 10%?
10%.
It is. Yeah.
Would that other field be 90?
Yes. Yes. I should have done that, I guess, but there we go. That one's very similar to one above, so I'm not going to do that one. It actually it's not, it can't be the same one, probably just got different numbers. Okay, this one is to do with bad samples, right? Samples that are not representative of the population. So let's see what's wrong with this one. A question was given on msn.com on March the 2nd on 2020, and it asked them, how good are you at math? And the answer that they got was 18% said they were really good, and they were going to use this information to compute a 90% confidence interval, right? Seems reasonable, except it's not. I could get a 90% confidence interval, right? I could put the numbers in. It's a single proportion. Oh, by the way, we're back to single proportions right now, right? So we've left differences, we're way back to single, right? I could do that, I calculate it, but I'm not going to, and I wouldn't. What's wrong with that sample? Physically wrong with that sample. You want to know how good Americans are at math, right? Their opinion on it. Do they think they're good at math? What's wrong with that sample? And it started right there.
It's only collected from people who visit that website.
Yeah. And we call that in the jargon self-selected, don't we? That's just the name we call to that type of thing. That's not a fair representation. Would you agree that a lot of Fox News people probably wouldn't go to that site? For starters. And all sorts of other people wouldn't go. So it's a bad survey. The data is biased, right? It's not a fair representation of every American. It's only a representation of Americans who go to that site. And isn't it only a representation of the people who go to that site and then bother to vote? Yeah, we got time. In a survey, 41% of randomly selected sample of 1,000 and change Americans said they did not get enough sleep. The margin of error for this was 3.5%. So I know that number and I know the margin of error. So I should be able to calculate the interval. Won't it be 41 take away that number, which is, based on the tiredness I am, 37.5%. And it finishes at 44.5%. Then I just added, subtract the margin of error from 41. Right, so I didn't really have too much to do there. Write a sentence to interpret that. So with a 95% confidence, we can say that the population of American adults, why am I picking adults? Because of that, right? Between 37.5 again and 44.5 would say they don't get enough sleep. Are we cool with that answer now? Now, do you think that we should be able to use this estimate to predict the percentage of college students who don't get enough sleep? I agree with the shaking of the heads. Brendan, tell me why not. I agree with you.
Because it was an estimate of the population. It was an estimate of American adults, not college students.
Right. And college students might not be exactly the same as the general population. Would it be reasonable to say that they're likely to be younger in general?
Yeah, and they probably have, well, their lives are a lot different than the rest of adults.
Yes. So if you know that the people that you're interested in are significantly different from the people that your general sample is from, shouldn't you be very careful about making the analogy that because it's true for all adults, it's also true for various subgroups of those adults, right? You know, I wouldn't use that data for 70 plus people either. Would you agree? They may or may not get enough sleep for all sorts of other reasons, right? So, yeah, that is my version of that.
So would it
Right.
violate or fulfill the fundamental rule?
Well, the fundamental rule is based on your sample, which says that your sample should be a fair representation of your population. I think this one here is breaking a different rule. I think that, I don't even know if this has a name, but isn't the rule that we're breaking here is using information about a population to predict what we think a subgroup of that population might be. Right? I don't think it's got a name, but I certainly wouldn't use it anyway. Well, I could also argue, I guess, that way. Would you agree using all adults to predict what college students sleep is a bad sample? Shouldn't you use a sample that's only got college students if that's what you were trying to find out? So I could probably argue it from that perspective as well, which then if I did would break the fundamental rule that your sample should be a fair representation of your population. So I did find a kind of workaround to kick it out for that reason. Time for last one. Yeah, we got time, don't we, Abra? What's my time like?
7 minutes.
Oh God, I get tons. Right, a poll conducted in America. Do you think the use of marijuana should be legal or not? In a nationwide poll of this many adults, 37% said they favoured it, and the margin of error was 3%. Oh, I don't think I want to do that one. Isn't that a direct copy of an earlier question, just different numbers? So nothing in there. Oh, that is interesting. I like this one. I almost missed it. You got to be really careful about this one because there's two numbers that you could confuse in your brain. Suppose that 500 different researchers across the world, right? Every single one of those researchers did the same thing. They all got a sample of 400 individuals, right? A nice random sample. And each researcher used their sample to compute a 95% confidence interval for the proportion who have blue eyes in the population. About how many of those confidence intervals will actually be working? Well, isn't the answer for a 95% confidence interval that 95% of the intervals will work? Well, 95% of 500. Which I can't do because it's far too late in the day, at least not successfully. So wouldn't that be 475? Which is 95% of the 500 should contain it. How many of that 500 will be wrong then? Is it not the other 5%? Now, since we don't have an unlimited amount of supply of money, can you imagine that there probably is never going to be 500 different scientists all collecting data about whatever it is? You're probably, if you're lucky, going to get 4 or 5, right? You know, somebody in America, 2 in Britain, 1 in China, right? That kind of thing. And if we're all using a 95% confidence interval, if we're really, really unlucky, couldn't we get one of these guys? And so couldn't you come to a conclusion that was wrong? And because so few people did it, you might still, there might be some conclusions that are going on right now, like what percentage of the population are left-handed? Let's just take that. It's not a biggie, right? If America did that research and they did it with Americans, and then the Japanese did that research and did it with the Japanese, and let's say Britain done it and China done it, right? Let's say they all did it 4 different times. Couldn't they come up with different numbers? In fact, I'm pretty sure they would. Would you be able to say for sure what percentage of the world was left-handed? Because couldn't Russians be a little bit different from the rest of us? Couldn't Nigerians be a little bit different? Could Koreans be a little bit different? So we have to be really careful when people collect data that you know what their sample is, because doesn't that reflect how confident you could be at the extension to the world, right? I wouldn't want to use American data for how far the world is. Would you agree the percentage of obese in America is much more than the rest of the world? So samples are important. And I think that's actually a really good place to finish.